Okay, so hi everybody. This is the second video for week 14 of Physics 46. And what we're going to do here is finish up the chapter on sources of magnetic fields. This is the chapter that we've been on for the last couple of weeks. So where we left off last time is we worked out this problem. We worked out these results here. So I'll start by recapping the problem and the result, and then we'll see how we can take this result a little bit further. So here's what's going on. We have a circular loop of current. That current is running in this direction around the loop. The radius of that loop is r. The loop itself, it sits in the xy plane, and the center of the loop is at the origin. What we're interested in is what the magnetic field created by this loop of current, what it looks like at this point right here, which is on the z-axis. What we found is, because of symmetry, both the x and y components of this field go to 0 because you get cancellation from opposite sides of the loop. We also found that the only non-zero component, which is z, bz turns out to be mu naught times I times r squared divided by 2 times r squared plus z squared to the power of 3/2. Okay? So I want us to take a look at this result in particular and see how it behaves in what's called the far field limit. So what that means is we're just really far away from the loop itself. In other words, our distance from the center of the loop, which we're calling z, is going to be much, much bigger than the radius of the loop, which we're calling r. So we'll see how that expression behaves in that limit. Okay, so we'll start with a sketch. Remember, we have the loop of current circulating this way, and then we have some point, which is up here, distance z away from the center of the loop. The radius of the loop we're calling r. Okay, so what we found is that bz is equal to, we have mu naught times I times r squared divided by 2 times r squared plus z squared to the power 3/2. Okay? So I'm just going to take a look at this part, r squared plus z squared to the power of 3/2, and try to expand it out just a little bit. Okay, so the first thing I'll do is I'll take just the part that's in parentheses and pull out a factor of z squared. Okay, so what we have is now z squared, and then the first term is r squared divided by z squared. So you see how if you distribute the z into that, you just get r squared back, and then plus 1, because if you distribute z squared times 1, get z squared back. Okay, if we take all of that to the 3/2 power, we'll have an expanded version of what we started with. So the next thing I want us to think about is, if we suppose that we're in the far field limit, which for our purposes means that z, this distance, is much, much bigger than the radius of the loop. Here's how we can simplify that expression somewhat. So we have z squared, and then we have r squared divided by z squared plus 1. Okay, well, if we think about it, r divided by z is going to be a really small fraction. It's going to be a lot less than 1 because the number on the bottom z is much bigger than the number on the top r. So r divided by z is some tiny number, much less than 1. And of course, if we square that, which is what's going on here, we get an even smaller number still. So basically, what's going on in the parentheses is some tiny number, much less than 1, plus 1. But, I mean, that's just approximately equal to 1 if we're using the far field limit. So we have z squared, approximate all of that as 1, and then take that all to the 3/2 power. So that's just z squared to the 3/2 power. If you multiply the powers, you'll get z to the 3rd, z cubed. Okay, so in other words, in the far field limit, all of this on the bottom here, next to the 2, is approximately just equal to z cubed. So what we have is mu naught times I times r squared divided by 2 times z cubed. Again, this is when z is much, much bigger than r. That's when this approximation holds true. The thing you should notice about that is that we have a 1 divided by z cubed dependence. In other words, the B field is falling off with distance, getting weaker with distance, not according to the inverse square of the distance, but according to the inverse cube of the distance. Okay, so that's how it works with current loops like this one. So to summarize that, in the far field limit, we have B is approximately equal to mu naught times I times r squared divided by 2 times z cubed. Okay, so it turns out this current loop is not just a random problem, it's actually very, very important for how magnets work in general. So let me try to show you what the connection is. So if we look at the B field that's produced by a current loop, which I'm showing you on this side of the screen, on the left, it's actually remarkably similar to the B field created by a bar magnet, which you're seeing on this side. And you've seen this picture before, we've gone through this already. But basically, with the current loop, we see in yellow the loop of current circulating this way. Remember how the B field lines should be oriented. Any kind of current should have B field lines which are going around it, okay? So we have a B field line going around the current loop like this, another one like this, and so on, okay? Well, that looks quite similar to the bar magnet, which, as you recall, has B field lines coming out through the north pole of the magnet and then looping back around into the south pole, okay? So in a similar way, with our current loop, the B field lines are coming out of that loop, coming around and then back through the bottom of the current loop. So that's the similarity. And in fact, they're so similar that we call this current loop a magnetic dipole. We call this a magnetic dipole. Why is that? Because it produces a magnetic field much like a bar magnet, which is a dipole. In other words, it has 2 poles, north and south, okay? This, in a lot of ways, has 2 poles, north and south. So that's a current loop. It produces a magnetic dipole field. And the way it works, as we just found, far away from a magnetic dipole, okay, the field, the strength of the B field, it follows an inverse cube law. It's a 1 over r cubed kind of dependence as far as how the strength of that B field gets smaller with distance. The last thing to note here is, okay, if this is a magnetic dipole, it has a north and a south pole to it, you might wonder about a simpler kind of thing, a magnetic monopole. So in other words, what if I could just like take the south pole itself and just isolate that away from the north pole of the magnet, right? It turns out you can't do that. Magnetic monopoles, isolated north or south poles, don't exist. So that's not possible. The simplest kind of magnet is actually the dipole. Monopoles don't exist. Okay, so the current loop helps us understand magnetic dipoles, which are going to be really important coming up. So let's do a couple more examples with the Biot-Savart law. In this case, we have half of a circle which is carrying some current. Here's what's going on. We have a wire that's bent into a half circle of radius r, and it carries a current I that's going along the wire. We have 2 long and straight wire segments that are connected to the half circular loop, as you see here, right? So basically, current flowing straight to the right, then through the half circle, then going out straight to the right, okay? What we want to do here is find an expression for the magnetic field at the center, which is point C on our diagram. So let's go through that, see how it works out. Okay, so start by making a picture. We have a straight segment of wire, we have a half circle segment, and then another straight segment, the current's flowing this way. So you might imagine that in order to calculate the total field, we should probably break it into these three segments, right? Try to analyze the field contributed by this segment, then the half circle, then this other straight segment as three separate pieces. And if you recall, the Biot-Savart law works like this. dB equals mu0 times I divided by 4 pi times r squared, and that gets multiplied by dl crossed with r hat. Okay, let's remember dl is what we call our current element, okay? It's a little segment of the wire that points along the direction of the current. On the other hand, r hat, that's a unit vector, and it goes from our current element to the point where we're calculating the field, which is right here, point C. So I'll label that point C. So let's take a look at this segment to start. Our dl, the current element, would be a vector kind of like this pointing to the right. I'll call that dl1. Let's call this segment 1 over here on the left. Okay, r hat, that would be a vector which points from this current element to the field point, which is also going straight to the right. So this will be what I'll call r1 hat. So notice the angle between them, which I'll call theta1, is 0. They're directly aligned with each other, okay? And as it turns out, that means the cross product between them is going to go away. It's going to go to 0. All right, let's do the same thing for this second part, where we have the half circular segment. Let's say this is our dl. I'll call that one dl2. So r2 is a vector going from this current element to the center of the circle. Remember, this is our field point right here. So this vector is r2 hat. Now, those are actually at a nice 90-degree angle, because one of them is going tangent to the circle, the other is going radially inwards. So the angle between these two, which I will call theta2, is 90 degrees. Let's also get a sense of what direction the B field due to that current element is going to be. So remember, we're doing dl crossed with r hat. So we're just going to use the right-hand rule as it applies to cross products once again. So we have dl going like this, up and to the right, so that's your right hand. Fingers pointing out like that. And then if you cross with r, I'm going to curl them down like this. Your thumb is going to be going into the page. So I'll say dB2, the magnetic field contributed by this half circle segment, is going into the page like this. Now finally, we're going to take this third segment, and we want to say dl3 is a vector going in the direction of that current, so it's to the right. But r3, that's a vector going from this current element to our field point. So that's pointing in the opposite direction to the left. So the angle between them is 180. That's what we have right there. Okay, so let's note that dB1 and dB3, the magnetic field contributed by these two straight segments of wire, are both 0 due to the fact that we're trying to cross two vectors that are parallel with each other in this case and anti-parallel in this case. So if you take the cross product of two vectors that are at 0 degrees with respect to one another, you get 0. Same deal with two vectors that are at 180 degrees. You take the cross product, you get 0. So the only contribution is coming from this part, the half circle. So the next thing we'll do is work out what that field contribution actually is. Okay, so next, I know dB2 is going into the page. So next I'm going to focus on its magnitude. The magnitude of dB2 is mu0 times I divided by 4 pi times r squared. And then basically, I'd be taking the magnitude of dl cross r hat to get the magnitude overall. So I have dl2 crossed with r hat 2 to be precise, right? Okay, a few things to note. Little r on the bottom, that's the distance between your current element and your field point. But in this case, that's just the radius of the circle, okay? So in other words, this is just mu naught times I divided by 4 pi big R squared. What I'm saying is the distance between your field point and your current element, R, lowercase r, is the same as uppercase R, which is the radius of the circle. Okay? So hopefully that makes sense, just the radius of the circle giving you that distance. All right, next we'll have a cross product which we'll evaluate. That's, okay, the magnitude of a cross product is the magnitude of the first vector, which is dl2, times the magnitude of the second vector. R hat is a unit vector by definition, okay? So it has length 1. So whenever we get to this step and we take the magnitude of r hat, it's always 1. And then we'll take the sine of the angle between them, but as we stated up here, that's a 90-degree angle. So 1 is a factor, and sine of 90 just gives you another factor of 1. Basically, we can just ignore those last two factors, they're both 1. So that means the magnitude of our B field overall is just going to be what we get when we integrate over dB2. Okay, so in other words, if this little current element is giving us this infinitesimal amount of B field, I'll have to integrate over all of those to get the total. And so, before we even evaluate the integral, it's going to be useful to identify what's constant. And luckily for us, there's a lot that's constant. Mu naught I, those are both constant, 4 pi. And then also capital R, that's a constant, it's just the radius of that circle. So what we have is mu naught times I divided by 4 pi r squared. These are the constants. I pulled them out, and then the only thing remaining inside of the integral is dl2. So we integrate over dl2. What does it mean to integrate over dl2? That means we will find the total length of this segment, which is a half circle, okay? So it's not a circumference, it's half of a circumference. So we have mu naught times I over 4 pi times r squared. A full circumference is 2 pi r, so half circumference is pi r. So we have pi times r going in right there. And we can cancel out the factors of pi and one of these factors of r, giving us mu naught times I divided by 4 times r. That's your B field, and as we said, it's going into the page. Okay, so this is the expression for the B field, and as we said, it's going into the page. Okay, so that's how this one works out. So to summarize, we found that the total B field is mu naught times I divided by 4 times r, and it's going into the page. All right. Let's do another example. Now this one, we can use a lot of the results that we just determined in the previous problem. And this one is going to involve some numbers, so you'll plug some things in. For this one, try it out, pause the video, and then come back to the video once you have your answer, and we'll compare. Consider the loop of current shown above, which consists of 2 connected half-circular segments, radius R1. That's the half circular segment on top, which is a little smaller, with the radius of 2.5 centimeters, and then the one on the bottom with radius R2 at 7.5 centimeters. The current in the loop is 3.65 amperes. We know the value of mu naught, that's called the permeability of free space, is 4 pi times 10 to the minus 7 Tesla meters per amp. So what you should do is find the magnetic field, both magnitude and direction, at the center of this loop, okay? And feel free to use any of the results from the previous problem because we are dealing with half circular segments once again. All right, so let's go through this. I'm going to draw the picture once again and just label everything in the way that it was shown on the diagram. Remember, we have the smaller half circle on top and a straight segment of wire connecting down to a larger half circle on the bottom, and then connecting back up with another straight segment of wire. We're interested in the B field at the center. The radius of this bigger half circle is R2, and the smaller one is R1. We have the current in this picture flowing counterclockwise, like this. And so we can basically just use the right-hand rule. Remember, the right-hand rule says if you take your thumb, okay, and you point it along the direction of the current, you'll kind of curl your fingers around that current like this, and that will show you the direction of the B field. So hopefully from that, it's clear that the B field is coming out of the page. Like let's say we do that for the bottom segment, we get a B field coming out of the page like this. If we do it for the top segment, we still get a B field coming out of the page. So overall, the B field is coming out of the page, which we indicate like this, okay? So if we label these segments, again, we have 1 on top, 3 is over here, 4 is over here, that's what I'll just call these, 3 and 4, and then 2 is the one on the bottom, okay? But as we saw before, B3 and B4 are both going to contribute 0 to our total magnetic field. The reason for that is if you do DL crossed with R hat for these two segments, you're going to find that they're pointing in the same direction, so you get 0. Okay, so remember how that works over here for the straight segments. Okay, so for the other two segments, we also have a result from the previous problem that is going to be useful here. Because for the half circular segments, we found that it's mu naught times I divided by 4 times R. And that's going to apply to, of course, segment number 1 and segment number 2 separately. And again, we found, I just showed you that B1 and B2 are out of the page. And the B field is going to be given by mu naught times I divided by 4R, using the previous result from the last problem, okay? So basically, we just have to add those two fields together, the contribution from B1 up here and the contribution from U2 down here. So the total B field is equal to mu naught times I divided by 4 times R1, that's going to be this contribution, plus mu naught times I divided by 4 times R2. It's going to be this contribution, okay? And to simplify that just a little bit, we have mu naught times I divided by 4 as a common factor, which you can pull out, and then you just have 1 over R1 plus 1 over R2. And now we're ready to plug in some numbers. So B, the magnetic field strength that we're looking for at the center right here, is equal to mu naught, which is 4 times pi, times 10 to the minus 7 Tesla meters per amp. The current is 3.65 amps, that's I. And then we divide out 4. And then we take in the brackets 1 over R1, which is 2.5 centimeters, or 2.5 10 to the minus 2 meters. And then we have 1 over R2, which is 7.5 centimeters, or 7.5, 10 to the minus 2 meters. Now the units are pretty simple. Amps cancel here and here. Meters cancel here and here. And we're just left with Tesla, which is our SI unit for magnetic field strengths. Crunching the numbers will give you 6.12, 10 to the minus 5 Tesla. Okay, so that's that example. And there's a lot more stuff you can do with the Biot-Savart law, more examples that you'll see on the homework. But that's really all that I want to show you as far as the lecture is concerned. Okay? So I think you've seen enough examples with the Biot-Savart law to do the homework problems. So that means we're going to get to the very last topic of this lecture, which is magnetic materials. And we're going to answer the age-old question right here. The idea here is we've discussed at great length how if you have a current, an electrical current running through a wire, that produces a magnetic field, and we've seen different ways we can calculate those types of magnetic fields. But again, what about bar magnets? What about just a chunk of material that has a magnetic field? What is going on there? It's not obvious that there's an electrical current in, let's say, a bar magnet that you can just hold in your hand. Okay, so let's discuss how to make that connection between what we know and magnetic materials. So basically it turns out that when it comes to a magnetic material, like a bar magnet, it really doesn't work any differently than what we've seen already. The fundamental idea still holds, that it's an electrical current that produces a magnetic field. That's still the case. And if we try to get a sense of what this idea tells us from the macroscopic point of view, it's basically, you have some wire, you run a current through it, and you get a B field. That B field loops around the wire. Again, Ampere's law or the Biot-Savart law can be used to calculate what that B field is, depending on the geometry of the situation. But the microscopic view, when we take a look at the microscopic level of atoms and molecules, we need to look at how charged particles, like electrons, are behaving. So as it turns out, the currents that are present when you have a magnetic material are actually created by the electrons within the atoms of that magnetic material. So if an electron, which is a negatively charged particle, is moving around inside of the atom, you have a tiny microscopic electric current because you have moving charge. And it turns out when it comes to electrons, there are basically two ways that you have this sort of moving charge. So for one, an electron doesn't just stay stationary within the atom, okay? In a rough sense, we can imagine the electron is orbiting the positively charged nucleus, kind of like a planet orbits the sun. This picture is grossly oversimplified and in a lot of ways wrong, to be honest, right? You need quantum mechanics to really understand how electrons move within the atom. But this is just a useful mental picture for now. Just imagine a negatively charged particle moving around in a circle like this. It kind of looks like a little loop of current, if you think about it. At the same time, the electron itself has a property called spin, okay? It's kind of like the electron itself is spinning on its axis, much like the Earth spins on its axis and also orbits the sun, okay? Again, that picture is grossly oversimplified and kind of wrong in some ways, but it's just a useful mental picture to see how we have electric currents even within an atom, okay? Just because of the motion of electrons. And if we're talking about the orbit of the electron around the nucleus or the spin of the electron on its own axis, both of those can be modeled as tiny little current loops because what you have is electric charge in some way moving in a circle. And that brings us back to the magnetic dipole. We talked about how if you have a loop of current, it produces a magnetic field, which are remarkably similar in how they look to bar magnets, right? With a north and a south pole. Okay, if you have an electron spinning on its axis, that's going to create B field lines, which go up and then loop back around through the bottom, much like if you had a south and a north magnetic pole there. And the same goes for the electron orbit. If the electron is orbiting the nucleus, you're going to see that B field lines, which loop up like this, through that orbit, and then come back around through the bottom, are produced. So the B field lines are that of a magnetic dipole. I also want you to remember this. If you have a magnetic dipole, like a loop of current, that's inside a B field, it's within an external B field, it feels a torque, right? There's a torque that's going to be acting on it, given by this formula right here. The torque is equal to mu cross B. This is what we call our dipole moment. It's a vector. Remember, if we have, let's say, this situation where there's current flowing in a circle like this, my mu naught vector is found by the right-hand rule, okay? So it looks like this. So I'll point my fingers in the direction of the current, thumb is in the direction of mu. Then, if I want to know what the torque that this thing is experiencing, I take mu cross B. So it's mu cross B like this. So it looks like it's going to be feeling a torque going like this in the clockwise direction. So that's what happens with atoms that have electrons circulating in them, right? They are little magnetic dipoles. If you put those magnetic dipoles in a field, it's going to feel a torque. And what does that torque do? Let's take a look. If this magnetic dipole feels a clockwise torque, it's going to move it so that it's oriented with the external B field. It's going to give it a torque until it aligns with the external B field. And so, magnetic dipoles, as it looks, tend to align themselves or want to align themselves with external B fields. And that is how we understand ferromagnetic materials. Okay, so any kind of bar magnet that you've been dealing with in the lab up until this point is a ferromagnetic material. And a ferromagnetic material is something that consists of tiny little domains. These domains can be anywhere between like hundredths of a millimeter, tenths of a millimeter, to maybe a millimeter in size. That's the typical size of these domains. And within each one of these domains, the electron spins are all aligned with one another. Okay? So in other words, all of the electrons within a domain, let's just pick this one out as an example. This is a magnetic domain. Again, its size is on the order of like hundredths of a millimeter to millimeters, somewhere in that area. Within that domain, all the electron spins are aligned. So there is basically a B field contributed by each one of those electrons. And each one on its own is pretty tiny and insignificant, but if you have a whole bunch of them where they're all aligned, they might add up to give you something that's noticeable. So that's what we see within each one of these domains, okay? You get a little magnetic field pointing in a certain direction. But what if we take this material, which for the moment is unmagnetized, because all of these domains are just in random directions, they're not really pointing in any particular direction. We can put it within an external magnetic field. So we take this magnetic material, we put it in an external magnetic field. Let's say that external magnetic field is going up like this. We'll call that B naught for the external magnetic field. Well, as we just saw, right, you put these magnetic dipoles in an external field, it tends to exert a torque on them, which makes them align with that external magnetic field. So now, if the field is strong enough, it can torque all of these into alignment. Now all of the domains are pointing the same way. And now your material is magnetized because all of these tiny little magnetic fields contributed by all of the electron spins within the material are going the same way. So when they're just scrambled and in random directions, they all cancel out because they don't point in any particular direction. But when they're all going the same way, they don't cancel out. And you get a large B field as a result. So now we've magnetized the material, and even if I take the external field away, it's still going to remain this way, magnetized, and creating its own strong magnetic field. Okay? So that's what it looks like when you take a ferromagnetic material, which is unmagnetized, and you magnetize it. Okay? You basically kind of force it to be magnetized by putting it in a strong magnetic field. Now, we can undo this whole process. We can take something that's magnetized and unmagnetize it. One way we can do that is just by heating it up, okay? So basically, if we heat this thing up in the magnetized picture, we're going to introduce a lot of thermal motion. In other words, these domains are going to jiggle, and if they're jiggling fast enough, it can knock any of these domains out of alignment. And it can, in other words, scramble everything so that everything is pointing in random directions like before. Okay, so we can magnetize something by exposing it to a strong B field. We can demagnetize something by heating it up. And by the way, ferromagnetic materials, one classic example of that is iron. Okay, iron is what ferromagnetic is actually named after. Okay, so let's take that picture and introduce a couple equations that describe what's going on. So to summarize, when placed in an external magnetic field, we're calling that external field B0. The material itself has what we call an induced magnetic field. In other words, there is a magnetic field created within the material as a result of that, and we call that field B induced. Okay? It turns out that the induced field is proportional to the external field. So in other words, if I expose my material to a very weak field, it's going to have a weak induced field. If I expose it to a very strong field, it has a strong induced field. Turns out they're just directly proportional to each other. In other words, B induced in the material is equal to some constant times B0, the external field. And we call that constant of proportionality the magnetic susceptibility of the material. And its variable is chi. Okay, so B induced is chi times B0. So ferromagnetic materials are defined by their large magnetic susceptibilities. They're very susceptible to being magnetized, which means chi has very large values. It typically ranges anywhere between like 10 to the 3 and 10 to the 5, depending on the exact material that you're using. And of course, the total magnetic field is the sum of the two, right? It's the external field plus the field we induce in the material. So the total magnetic field, which I'm just going to call B, is the sum total, which is B0 plus B induced. And these are going, by the way, in the same direction, so we can just straight add them together. So we have B0 plus B induced, but we said earlier that B induced is chi times B0. It's our susceptibility times our external field. So the total field is just 1 plus chi times B0. Okay? So that's the result. And that's what magnetic susceptibility is. If you work with these types of materials, you're going to be looking up numbers like this in tables a lot. Okay? Okay, so moving on. It turns out what I just described to you, ferromagnetism, is just one type of magnetism. It turns out there are other types which are a little bit more subtle, it turns out, to understand. So we'll just run through this real quick, get a qualitative picture. So starting with ferromagnetic materials, which we just covered, in a ferromagnetic material, you have large-scale magnetic domains. I mean, a millimeter might not seem that large, but compared to the size of an atom, that's incredibly large, right? So the magnetic domain is on the order of like, hundredths to tenths to maybe 1 millimeter. And as we've seen, these magnetic domains will align with an external B field. And even if you remove that external B field, those magnetic domains will remain in that same alignment. So you can magnetize the material this way. These are very strong magnets, right? If you want to create a strong magnet, you want to use a ferromagnetic material. There are only a handful of ferromagnetic materials out there. Again, iron is one of them. Not every metal is a ferromagnetic material. Most metals are not. Okay, so this is a special type of metal. Okay, it's pretty rare. Okay, so one way we can define ferromagnetic materials is susceptibility chi being much, much greater than 1. Very large values. Then next, we have something called paramagnetic materials, paramagnetism. So this is a much weaker form of magnetism, and here's how it results from the behavior of atoms. Basically, you have microscopic magnetic dipoles, but they're not organized into these large domains, okay? It's just individual dipoles. So those individual dipoles will align with an external B field, just like in the case of ferromagnetism, but they don't tend to get stuck in that alignment. So in other words, if you expose a paramagnetic material to an external B field, it will align itself with that. But if you turn off the external B field, it quickly just re-randomizes. And these are characterized by being weak magnets. So chi is a lot less than 1 when it comes to these paramagnetic materials. And this table shows you an example of just a few. So like aluminum, right? Chi is like 2.3, 10 to the minus 5. Very small values compared to, again, like ferromagnetic materials. And then finally, we have something called diamagnetic materials. And these also consist of microscopic little dipoles, but in this case, they align against the external B field instead of aligning with the external B field. So in this case, you'll have chi, which has a negative, but relatively small value still, like we see here. So examples would be like copper, bismuth, with these sorts of susceptibilities, okay? All right, so that's just a little bit about the different types of magnetism. And one kind of interesting technological application of ferromagnetism is creating electromagnets. Okay, so an electromagnet is basically a coil of wire that's wrapped tightly around a ferromagnetic material. Typically, it's going to be iron that we use for the cores of electromagnets. So we can do this in different shapes. We can do this with a solenoid. So remember, we've seen solenoids before. These are wires that are wrapped into a cylinder tightly with many, many windings for the entire length of the solenoid. All we're doing is putting a chunk of iron, a cylindrical chunk of iron inside of that solenoid. Okay? We can also do it with a toroid, where we have a toroidal shape of iron, so it's kind of shaped like a donut with wire wrapped around it many, many times. Okay? So in this case, the current in the wire, that's going to be our so-called external B field B naught. That's going to induce a B field within the ferromagnetic material, within the iron core. And again, that B field that we induce, because chi is so big, can be really, really large compared to the B field created by the current running through the wire, okay? So in other words, we're enhancing the strength of the magnetic field created by this current running through the wire by many, many orders of magnitude. It can be upwards of like 10 to the 5 times stronger if you have a solenoid with an iron core compared to a solenoid just filled with empty space. So remember, this is one of the strategies we can use to create stronger fields in the laboratory, right? One way is to take a piece of wire and wrap it up very tightly. So all of the fields created by each turn of wire tend to amplify each other, but also by using ferromagnetic materials, we can amplify the B field even more, okay, and get B fields of like tens of Tesla using this sort of method. And then the last thing I'll talk about here is magnetic data storage, okay? So here we're talking about things like magnetic tape or old school hard drives, which relied on magnetic materials. These days, hard drives tend to be solid state and based on slightly different physics, but this is an important concept just for understanding how we store data onto a hard disk or other type of substrate. So a few examples here. I said hard drives, right? Old school hard drives use magnetic disks. We have magnetic strips on credit cards. When you swipe a credit card, there's some data stored on a magnetic strip. And then audio and video cassette tapes, which are, again, not so common these days, but they use this sort of idea. So remember, when it comes to a ferromagnetic material, it consists of tiny little magnetic domains, and the orientation of those magnetic domains, which way the B field is pointing within that domain, can be flipped, right? Because if you just expose it to a strong external field, you can kind of get it to align in whatever way that you want. So we can use this to our advantage to store data, in particular binary data, with just ones and zeros. You can represent a 0 with a magnetic domain that's facing down, and then you could represent a 1 with a magnetic domain that's facing up, right? And that's how we can store a whole bunch of ones and zeros if our tape or hard disk or whatever it is consists of a lot of these different domains, which can store a lot of different ones and zeros. We can also read out what's going on. If we have like a strip of tape right here with a lot of different magnetic domains, we can read all the ones and zeros out using electromagnets. And I'll show you how that goes with this animation. Okay. So basically, if I sort of take an electromagnet and run it over the magnetic domains on my tape, I can induce some current to start flowing in that electromagnet and therefore read out the data. I can also use an electromagnet to overwrite the data, right? So I can like take a magnetic domain that's facing up and I can flip it down, or I can erase a bit by using electromagnets, okay? Again, nowadays the technology is a little bit more advanced than this, but ferromagnetism is very important in how data is stored, at least in the last 20, 30 years. So I think that's it for this lecture. As usual, we have a bunch of practice problems at the end, so feel free to work through these as you study. And remember, the test is coming up in 2 weeks. It's going to be on Monday, May 2nd. So I'll end it here, and next time you see me, we're going to be on the next chapter, which is chapter 13, Faraday's Law. So I'll see you then.